Today we're looking at the second half of section 4.5. So remember on Friday we talked about U substitution, which was an integration technique that allows us to integrate things that would have used the chain rule. On today's lesson, we're looking at that same thing. So still U substitution, but now we're looking at what it means to have a definite integral. So remember that our definite integral means that we have bounds, or that we have a point that we're trying to plug in. So the first part of it is going to be exactly the same. We're still just going to choose our U, take the derivative of both sides, and then substitute back in for our integral. The part that's different this time is that because we have bounds, those bounds are just going to be in terms of x. We need them to be in terms of U now. So we're going to change the bounds. And then lastly, we're just going to integrate as normal. So on our first example, we have the integral from 0 to 1 of x squared plus 1 cubed dx. So just like we would on Friday, I'm first going to set up my U substitution. I need to pick my U. Again, notice that we have something being cubed and we have an expression on the inside, so that expression is a good indicator as to what my U is going to be. I am then going to take the derivative of both sides, and we get 2x dx. So again, remember that here I'm going to have U cubed. My dx is going to become my du, so that's good. And my x is taken care of, but I don't have a 2 in my integral, so we need to move that to the other side. So I divide by 2. So we end up with the integral of 1/2 U cubed du. Now what's different about this one than what we talked about on Friday is now notice that we have a definite integral. So we have bounds. But these bounds are in terms of what it is for my x, or when I'm taking the integral with respect to x. Now, since we're taking the integral with respect to U, we need to figure out what those new bounds would be. And the way that we do that is just by using the substitution that we set up here. So notice that I have an equation that has U in terms of x. We already said that my bounds are in terms of x, so basically what we want to do is we want to say what will U equal when x is 0, so my first bound, and we get 1. And then we want to say what will U be when my x is 1, so my second bound, and we get 2. So now I'm going to rewrite the integral from 1 to 2. I'm going to move my 1/2, because it's a constant, out to the front, and then we can just integrate as normal. So we have 1/2. I would add 1, so I get 4. So I have U to the 4th divided by 4, and we're integrating from 1 to 2. Now, what's nice about our definite integral is because we're actually plugging in numbers this time, and we changed our numbers, we don't have to worry about plugging our x's back in. We're just going to integrate as we normally would, but just with our u's. So notice that I can bring my 1/4 out, so I would get 1/8, and then we will plug in 2 to the 4th, and I'm going to subtract 1 to the 4th, which is just 1. So 2 to the 4th gives us 16, minus 1 gives us 15, and then times 1/8, we get 15/8. And we would have gotten the exact same thing had we not changed our bounds and then just substituted this x squared plus 1 back in here and left my bounds the 0 to 1. And you can do it that way. It just ends up being a little bit longer and more complicated than just going ahead and switching the bounds. So let's look at another example. So notice that we have the square root of 1 plus 2x squared on bottom, and then we have an x on top. Right now our problem is that we have a square root and we have stuff or an expression inside of our square root. So, like we've been talking about, my square root would be my outside function, and my stuff on the inside would be my inside function. So I have u equals 1 plus 2x squared. So I'm letting my u be the stuff that's on the inside of my radical. Then I'm taking my derivative, and we get 4x dx. Again, we don't have a 1/4 over here, so I'm going to divide by 4. And now we can set up our integral. Again, we need to change our bounds. So if u equals 1 plus if x is 0, we get 1. And if x is 2, we get 2 squared, which is 4, times 2, which is 8, plus 1, which is 9. So now we're going from 1 to 9. Rewriting this, pulling my 1/4 to the front. This would be the same thing as u to the negative 1/2. And then from there, we can just use our power rule. So I would have negative 1/2 plus 1, which is 2/2. So we get a positive 1/2. And then we need to divide by our 1/2. We're integrating from 1 to 9. And remember that since I went ahead and switched my bounds, we don't have to plug in for x, which is nice. Remember that dividing by 1/2 is the same thing as multiplying by 2. 1/4 times 2 is going to give us a 1/2 on the outside. And then I'm going to plug in 9. Well, 9 to the 1/2, which is the same thing as the square root, is 3. And then 1 to the 1/2, which is the same thing as the square root, is 1. So this gives us 1/2 times 2, which is 1. And so that's the answer. Alright, so on this next one, we don't necessarily have a definite integral, but notice that they say to find the equation for f of x through the given point. So it's technically a definite integral because they give us a point that we're needing to plug in. However, we're not going to have to change any bounds or anything this time because it's given to us as a point, which means that whenever we do the u sub, we will need to substitute our x's back in. And then remember that that f of 2 equals 7 is our initial condition, and so we can use our condition to solve for c. So notice that they give us f prime of x, but they're wanting an equation for f of x, so we need to work our way backwards. So to get that, we would take the integral of f prime of x dx. We plug in our f prime of x, and notice that we have a square root. There's stuff inside of our square root, so we are going to need to use u substitution. So I'm going to let my u be 8 minus x squared. And lucky for us, everything is kind of sucked up into our u sub, so we don't have to worry about dividing out by anything. So we have the integral. My negative 2x dx is taken care of by my du, and then my square root is going to become the square root of u. Remember that the square root of u is the same thing as u to the 1/2. If I add 1 plus 1/2, we end up with 3/2. So we have u to the 3/2 divided by 3/2. And because this is not a definite integral, I do have to add my plus c. Remember that dividing by 3/2 is the same thing as multiplying by 2/3. But because, again, remember we need to be able to plug in our condition, we do have to convert it back to x's, because this condition is in terms of x's, not in terms of u's. So in order to solve for my c, I need to plug that back in. So I would have 8 minus x squared to the 3/2 plus c. And notice this is the same thing as 2/3. My exponent of 1/2 is going to give me a square root, and then it's raised to the 3rd power. So that would be my general answer if we're wanting a specific answer using this condition. Remember, I'm going to plug in my 2 for my x. We're going to set it equal to 7. So we have 2/3 times the square root of, well, x squared, so 2 squared is going to give me 4. 8 minus 4 is 4, so we end up with 4 to the 3rd plus c. So notice that 4 to the 3rd is going to be 64. The square root of 64 is going to be 8. So we have 7 equals 16/3 plus c, which means that c equals, if I subtract 16/3, well, 7 converted to a denominator of 3 would be 21/3. So 21/3 minus 16/3 gives us 5/3, which means that we can write out our answer. So f of x is going to equal, so notice that both of these are going to be over 3, my function and my c value. So it's just easier if we write it as 5, because that's my c, plus 2 square roots of 8 minus x squared cube all over 3. And you could also just write this as a 1/3 to the front. But since they're both being divided by 3, we might as well make it look a little bit nicer. And so that would be our specific answer for that differential equation. Alright, so on this next one, again, going along with the square roots, we have the square root of 2x minus 1 on bottom and an x on top. There are 2 different ways to approach this problem. I'm going to show you one, and then there is another way in your book, and I'll briefly show you what you would do for that one. So, again, sticking kind of with our pattern, I'm going to let my u be the stuff that's on the inside. I take my derivative. I don't have a 2 there, so I'm going to divide. And I get 1/2 du equals dx. Now, you might be thinking, oh wait, our derivative this time does not have an x in it, and you would be right. And that's why this one is a little bit different. So the way that I would approach this problem is, again, just kind of like with our bounds. We have this equation that relates u and x, and I have an x up here. I'm needing to substitute my x for something that has u's in it. Well, we can treat that just like we would treat any other equation. I can add 1 and divide by 2 to get x. Because then, if we do that, when we substitute, notice that on top, it's just 1/2 u plus 1 divided by the square root of u times 1/2 du. Well, because we just have a square root of u on bottom, we can simplify that. And then we also need to take care of our bounds. So I have u equals 2 times 1 minus 1, which still gives us 1. And then I have 2 times 5 minus 1, which gives us 9. So I'm going from 1 to 9. Now notice that we could pull this 1/2 to the front and this 1/2 to the front, so we end up with a 1/4 in the front of our integral. And then if I have u divided by the square root of u, remember this would be u divided by u to the 1/2 plus 1 divided by u to the 1/2 du. Well, this is u to the first. If I take 1 and I subtract 1/2, I end up with 1/2. And then here, this would just be u to the negative 1/2. Again, all multiplied by du. And then from there, it's going to be just like with any of our other stuff. I have 1/4. I need to add a 1, so I would get 3/2 here. So u to the 3/2 divided by 3/2. And then here we would add 1, we get 1/2, so we would have plus u to the 1/2 divided by 1/2. And I'm evaluating from 1 to 9. So my 1/4 is still hanging out on the front side. From this point, you could just plug 9 in first, plug all that into your calculator, and then subtract 1. I'm going to do it by hand. So notice that dividing by 3/2 is the same thing as multiplying by 2/3. If I plug in 9 here, 9, the square root of 9 is 3. 3 cubed is 27. Plus dividing by 1/2 is the same thing as multiplying by 2. I have times 3. Then we're going to subtract off, plugging in 1. So again, we have 2/3 times 1 is just going to be 1, plus 2 times 1 is just going to be 1. So 2/3 times 27 is going to be 2 times 9, which is 18, plus 2 times 3 gives us 6, so we get 24. And then minus 2/3 plus 2, finding a common denominator, that becomes 6/3, so we get 8/3. And then simplifying that, multiplying by 1/4, we should get 16/3. Now, like I said, there is another way that you can do it, and this is the way that your book does it. So if you wanted to follow along with how they do it, you can look in section 4.5. But the way that they do it instead is by letting u equal the entire denominator. so 2x minus 1. And then they square both sides, so they get u squared equals 2x minus 1. And then they take the derivative and do the u substitution that way. So again, you'll end up with the same answer because they used a different u. Their bounds are going to be different than mine. However, you do end up with the same answer. So you can do it either way. Alright, so let's look at one last example of our definite integrals with u sub. We have an e to the negative x squared divided by 2 and an x on the outside. Again, if I have an e to something, most of the time your exponent there is going to be your u. So I get u equals negative x squared divided by 2. So du equals, I would multiply by 2. 2 times 2 is just 1, but I still have a negative. So negative x dx. I don't have a negative in my integral, so I need to move that to the other side. And we get dx. So my x, I dropped an x over here, x dx. So my x and my dx get taken care of by that negative du. And then I still have an e to the u. Again, we need to take care of our bounds. So notice that if I plug in 0, we get 0 divided by 2, which is just 0. And then here, square root of 2 squared is just 2. 2 divided by 2 is 1. And then we just have a negative. So we get negative 1. So we have, again, remember, we do need to put these in the same order that I plugged them in here. So here, I plugged in 0 and got out 0. I plugged in square root of 2 and I got out negative 1. I can pull this negative because it's just a constant out to the front. And hopefully we recall that when I'm taking an integrand, we want the integral bounds to be from smallest to biggest. And we looked at a theorem that allowed us to, if these aren't in the correct order, remember it's going to equal the same thing as the negative of negative 1 to 0. Well, since I already have a negative there, a negative times a negative gives me a positive. So then we just have e to the u du. Taking my integral, the antiderivative of e to the u is still just e to the u, and we're plugging in negative 1 to 0. Again, remember that because I went ahead and switched my bounds to be in terms of u, I don't have to plug my x's back in, which is nice. So then we plug in our top bound first. So we have e to the 0 minus e to the negative first. E to the 0 gives us 1 minus 1 divided by e. Or if we found a common denominator, we could do e minus 1 divided by e. Either one. Alright, and then the last thing that we're going to look at are even and odd functions. So remember that an even function is anything that has a degree, which again, remember, is the highest exponent. That is even. That's a polynomial. And an odd function is going to be a polynomial that has a degree that is an odd number. Remember that our trig functions can also be even and odd, but our like x squared and x cubed are going to be the most straightforward. And the reason that we're looking at these is because remember that our even functions are going to be symmetric around the y-axis, and our odd functions are going to be symmetric around the x-axis. So remember that when I'm looking at these, if I looked at the graph of x squared, we get a U-type shape because it's going to be a mirror over this y-axis line. So when we're looking at the integral of that, notice that if my bounds are basically a reflection over the x-axis, so notice that we're going from -8 to 8, we would be looking at those two areas here. And when we're looking at those two areas, because we're symmetric about this y-axis, notice that these two areas are going to equal the same thing. So instead of integrating all of that, we can basically cut it in half and just say that it's going to equal double. So we don't have to do quite as much work. Now, on the opposite end, if I have a cubic graph, remember that my graph is going to look kind of like my little S shape. And we're going from -4 to 4. So when we look at that graph, again, pretending that it was nice and symmetric, it's symmetric across my x-axis. So this area and this area have to be equal, okay? But notice that because my first area is negative and my second area is positive, when I integrate these, they're basically going to undo each other, and so we're going to end up with 0. And so that's just nice for us to think about. If I have something that's an even or odd function, sometimes we can break it apart or kind of simplify the integral so that we can do it a little bit easier. Also, sometimes we might see it given to us as a graph, and they give us information about one side but not the other. Well, then we can just multiply that side by 2. Or same thing here, if we know information about one side but not the other, we know that it has to be a reflection, and so again, we can kind of use that property to help us evaluate the integral if we need to. And here is our homework.